Equilibrium. All right, most of the reactions that we've been looking at now have been going to completion, or at least we say that we've been going to completion. Classic example is combustion, right? Once I start burning something, that thing will burn until all of the reactants are used up, and all I have left are products. So this is a classic graph of a reaction that goes to completion. I start it with 100% reactants and no products. As time goes on, and we talked about this in the last video, the reaction will start to go very quickly at first and then gradually level off. First, I'm going to have this huge amount of burning that's going to burn up, and then toward the end, I just have these embers that are still there. The rate of the consumption of my log, my Yule log, is going to go down. Most reactions actually do not go to completion. They reach what we call as a state of equilibrium. And that equilibrium is a situation in which both reactants and products are present, but the concentration of those reactants and products do not change over time. So it has to happen in a closed container. It has to happen at a constant temperature and pressure. And what happens is that when I reach that equilibrium point, I'm going to have the rate of my forward reaction equaling the rate of my reverse reaction. So the way that we write reactions that go to equilibrium is that instead of a single-headed arrow, we have a double-headed arrow that shows the reaction going both ways. So here's a couple of examples that I have. The first one is solubility. Right? So I have an ionic compound or some solid, could be a lump of sugar, that starts out, and I first have my water, and I just have my solid in the corner. So at the initial state, all I have is undissolved solid and water. So my reactant is my undissolved solid, my product is dissolved solid. After time, I start to dissolve, and you can see this starting to get smaller as my solid starts to dissolve in the water. If I'm looking at my reaction, my reactant solid to dissolved, all I'm doing is having my solid starting to dissolve. As I go on, what starts to happen is that I will have things dissolve, but I will also have things undissolve. So I have my solid dissolving, but I also have this little arrow going back, showing that some of the dissolved particles are now undissolving, coming out of solution. When you get to equilibrium, I now have a situation in which I have my solid and my dissolved particles, and the length of my forward arrow is equal to the length of my reverse arrow. That's a way of being able to show that the rate of my forward reaction is the same as the rate of my reverse reaction. In practical terms, that means for every molecule that dissolves, goes into solution, I have a molecule that comes out of solution. So it's kind of like you're at a situation where you have as many people enter a building as leave a building, so that the concentration of people inside and out remains constant. If I'm using an example of the cafeteria, when we could go into the cafeteria, at first everybody's going into the cafeteria. That's all of the reaction is going into the cafeteria. As lunch is going on, you have some people beginning to leave the cafeteria and some people coming in late. And then at lunchtime, during the height of lunchtime, you might have just as many people leaving as entering. I'm not saying that there's nobody in the cafeteria, nobody outside. It's just that the number of people remains constant inside as it was outside. And then finally, at the end, you have everybody leave, but that's a different story. So when I reach equilibrium, the numbers, the concentrations stay constant, but that's not saying that if something was a solid, it's always going to stay a solid. It's really saying that for every molecule that's a solid that goes into solution, I have one that leaves. Evaporation is another example, right? So again, a closed container. So I have my bottle and I filled it up partly with water. So initially I just have water. After a while, some of the water begins to evaporate, so I have water going to gas, right? Then I'm starting to have some of the molecules fall back down again. And so I have a small arrow that goes gas back to water. I'm beginning to see condensation. Until I reach equilibrium, at the rate of evaporation equals the rate of condensation, I have water going to gas, I have gas going back into water. Classic example of this is in the shower, right? Especially in the wintertime, you see this. So when you first turn on the hot shower, there's nothing in the air. At least you can't see anything. Then as you take a shower, especially if you're like, oh, it's been a long day, I'm going to take a hot shower, the bathroom starts to steam up, right? So that's all the water evaporating and you're starting to steam up and it's starting to billow. If you're in the shower long enough, which you shouldn't be getting to this point, but if you're in the shower long enough, what starts to happen is that it starts to rain from the ceiling of the shower. What happens is that the rate of evaporation now starts to get so much so that there's so much steam in the air that it starts to condense and it starts to precipitate back down again. Usually collects on the cold surfaces like your mirror and your toilet and the ceiling of your shower. But at that point, for every stuff that's going into steam from your hot shower, you have water coming down from your ceiling in the form of rain. So that's another practical example of equilibrium. So again, when the reaction is at equilibrium, the rate of my forward reaction equals my reverse reaction. So the rate orders, those things that were experimentally derived that we went through last video, where I'm doubling the concentration of a reactant and seeing what happens, that actually just gets obliterated, because if my rate of my forward and my reverse reactions are equal, then basically what I'm saying is that the time it takes to go this way equals the time it takes to go this way. So it's a one-to-one exchange, and so any multi-step aspect to it that could complicate things becomes obliterated because it's going to be same no matter which way I'm going. So we don't use rate orders. Those don't have to be experimentally derived. We use a more useful measure, which is called the KEQ. So the KEQ is the ratio of products that are created over the ratio of reactants that are lost. Or actually, at equilibrium, the concentration of products that I have over the concentration of reactants that are there. So here are some graphs of what something can look like at equilibrium. I can have a situation where when I reach equilibrium, and the way that I know from a graph that I've reached equilibrium is that the slopes of my reactants and products concentrations are horizontal, right? So it's a zero slope. There is no change. At the beginning, I have a steep change, and then it levels off. Where it levels off is when I've reached equilibrium, because the concentration, that's my y-axis value, the concentration of my products and reactants remains unchanged over time. So time on the x-axis, concentration on the y-axis. So I can have a situation in which when I reach equilibrium, not many of my reactants have been converted to products. I don't have that high of a product concentration. In that case, because my KEQ value is equal to the proportion of my products over my reactants at equilibrium, because my products are in the numerator, I'll have a small numerator and a large denominator. My KEQ value will be low and it'll be less than 1. If they're about equal to one another, then my KEQ value is about 1. And if they're much, much greater, like a lot of my reactants get converted to products, then my KEQ value will be greater than 1. The greater my KEQ value, the more products I have made when I reach equilibrium. Right? So one of the things that a KEQ value can tell us is that given the conditions that I'm doing things in, how much product can I expect to make? So it's fine-tuning that expected yield. Stoichiometry assumes that you are going to completion. Equilibrium puts a real-life factor on it, saying, well, you don't quite make 100% product. You get to this, and so it fine-tunes our expectations. So how do I get my KEQ value? The KEQ value, if I write my reaction as smaller case a, capital A, plus little b to big B, and so forth, then basically what my reactants are still on the left side, and my products are still on the right side. So even though I have a forward and a reverse reaction, The things that originally were reactants are still called reactants. Even if I go for my products to create reactants, these are still products, these are still reactants. The lowercase letters are coefficients. Those are the ones that are used to balance the equation. And A, B, C, and D in capital letters are the actual molecules. This double-headed arrow again shows that my reaction is at equilibrium. So if one of the arrows is longer than the other, I'm not at equilibrium yet. I might be somewhere in mid-process, right? So if my forward arrow is longer than my reverse arrow, then it could be a situation in which, just a minute, I am here in the process, right? So I've yet to reach equilibrium, or I'm here. It doesn't matter what my final KEQ value is. If my forward arrow is longer than my reverse arrow, it means I'm not at equilibrium. So this is a reaction that's reached equilibrium. My KEQ value, which is the constant that is dependent on a specific temperature and pressure and reaction, that numerical value is going to be equal to the concentration of my products over the concentration of my reactants. So just a reminder that brackets around something mean concentration of, and the concentration units are molarity, big M. And because it's concentration, it can only be a gas or an aqueous solution. Solids or liquids just have a 100% pure concentration all the time. And then the coefficients become powers, right? So say that this coefficient right here was a 2, that would mean I would take the concentration of C to the second power. So coefficients become powers, and then I have my reactants underneath my products. So my products over my reactants. And that's how you calculate the KEQ value. So again, if my KEQ value is high, that means that when my reaction reaches equilibrium, I have a high concentration of products. I have most of my reactants converted to products. And if I have something that's low KEQ value, it means that not much of my reactants has converted to products. So an example would be sugar dissolving in tea, right? It's a temperature dependent thing. If I have very cold tea and I put sugar in, my KEQ value is going to be very small because not much of my sugar will dissolve into my tea before I reach equilibrium. If my tea is really hot, then I will have a high KEQ value because more of my reactants will have been able to convert to products.